Yes. So last time we started with acidic nature of alcohols and phenols. What I told you, let us revise that. I told you that alcohols and phenols both are acidic in nature. The reason is oxygen is more electronegative than hydrogen. Therefore, OH bond is polar, and the polar bond breaks heterolytically, releases hydrogen as H plus ion, and this is the reason they are acidic. Now, since they are acidic, they will react with reactive metals like sodium, potassium, calcium, aluminium, and lead to the formation of corresponding salt and liberate hydrogen gas. We gave, we considered equations for that. Alcohols as well as phenol, they react with reactive metals, form salt, and liberate hydrogen. Now, since they are acidic in nature, it means they are supposed to react with bases to form salt and water. But when they are reacted with aqueous NaOH, phenol reacts and leads to formation of salt and water, but alcohol does not react. Now, these two reactions prove that phenols are stronger acids than alcohols. So, so far we have considered proofs for acidic nature, proof for stronger or weaker acidic nature in case of alcohols and phenols. We have not considered reasons so far. Now, in today's class, we'll take up why are phenols stronger acids than alcohols. Then we'll also consider, if we consider primary, secondary, tertiary alcohols, what is the order of their acidic strength. First, I'll explain, then I'll dictate you, right? See, how strong is, we'll first take up alcohols. How strong, what is the acidic strength of an alcohol will depend on how easily H is released as H plus ion. Means if the loss of hydrogen as H plus ion is easy, acidic strength is more, right? Now, when will the release of hydrogen as H plus ion be easy? If this bond between oxygen and hydrogen is more polar, if OH bond is more polar, then release of H plus will be easy, acidic strength will be more. Now, listen very carefully. If alpha carbon atom is attached to 3 alkyl chains, it is tertiary alcohol, 2 alkyl chains, secondary alcohol, 1 alkyl chain, primary alcohol. All alkyl groups have electron releasing inductive effect, that is plus I effect releasing. Due to plus I effect, this electron density will be further passed on to oxygen atom, that is plus I effect will increase electron density at oxygen atom. When electron density at oxygen atom increases, polarity of OH bond decreases. Think of this. When electron density at oxygen increases, electronegativity of oxygen will decrease. Therefore, polarity of bond will decrease. Release of H plus will become difficult. That is, acidic strength will decrease. Now look here. if alkyl groups, if alkyl groups attached to alpha carbon atom are more will be in tertiary, then plus I effect will be more. Electron density at oxygen will be high. Polarity of OH bond will be less. Release of H plus will be difficult. And that is why acidic strength will be less. It means tertiary alcohol will be least acidic, primary alcohol will have maximum acidic strength. First we'll write this much, then I'll keep on explaining and dictating you. Right on. Acidic strength depends on how easily H atom of hydrogen atom of OH group is released is released as H plus ion, is released as H plus ion. In alcohols, plus I effect, electron releasing inductive effect, plus I effect of alkyl groups increase electron density at alpha carbon atom, which decreases polarity, of OH bond, so that the release of H plus ion becomes difficult and acidic strength decreases. More the number of alkyl groups attached to alpha carbon atom, more is their plus I effect, more is their plus I effect, more is the electron density at oxygen atom, lesser is the polarity of OH bond and lesser is the acidic strength. That is why acidic strength of alcohols is in the order primary more than secondary more than tertiary. Primary more than secondary more than tertiary. Now look here. This is alcohol and this is water. In alcohol, this has plus I effect, alkyl chain. But there's no plus I effect in case of water. It means if we apply the same concept of plus I effect, it means water will be a stronger acid compared to any alcohol. Right on, next paragraph. On the basis of above reason, water is a stronger acid. Water is a stronger acid than alcohol. Now I'll explain about acidic strength of phenol. Naturally will be in comparison with alcohol. See, in alcohols, alpha carbon atom is sp3 hybridized. In phenols, alpha carbon atom is sp2 hybridized. sp2 means more electronegative than sp3. And due to more electronegativity, electron density at oxygen atom will be low in phenols than in alcohols. Low electron density oxygen means polarity of OH bond is more in phenols than in alcohols. This is the reason phenols are stronger acids than alcohols. One thing more, We have already done resonating structures of phenol in first chapter. In those resonating structures, if you turn pages and look at those structures, you'll find in three resonating structures, there is positive charge at oxygen. Positive charge at oxygen in phenol again means low electron density at oxygen, more polarity of OH bond, easy release of H plus, and therefore more acidic strength compared to alcohol. Now write down in the next paragraph. Alpha carbon atom in phenols is sp2 hybridized, and therefore more electronegative than sp3 hybridized alpha carbon of alcohols. Due to resonance also, oxygen atom in phenols carries partial positive charge. Due to this, OH bond in phenols is more polar, so that release of H plus ion becomes easy. That is why phenols are stronger acids than alcohols. Now, I'm giving you one more reason for comparison of acidic strength of alcohols amongst themselves, comparison of alcohols and phenols. First, I'll explain. After that, I'll dictate. Look here. Alcohol, after releasing hydrogen as H plus, will give this ion, which is called alkoxide ion. Phenol, after losing hydrogen as H plus ion, will lead to the formation of this ion called phenoxide ion. How strong the acid, how strong the strongly acidic will the alcohol or phenol be, can also be explained on the basis of stability of the ion formed after losing H plus ion. I'll repeat in other words. After losing H plus ion, how stable is the ion form, alkoxide or the phenoxide ion? On the basis of the stability of the ion formed, we can explain acidic nature of alcohol or phenol. See, after losing H plus ion, if stability of the ion formed is more, then release of H plus will be easy and acidic strength will be high. On the other hand, if stability of the ion formed is less, its formation will be difficult and acidic strength will be low. Remember, whichever ion it is, whether it is positive ion or negative ion, if charge in an ion is accumulated at one particular atom, one particular point. This is called accumulation of the charge, and accumulation of charge decreases stability of the ion. It's opposite. If the charge in any ion, positive or negative ion, if the charge is scattered, dispersed on different atoms, then stability of the ion increases and its formation becomes easy. Now, alcohol, after losing H plus ion, forms alkoxide. In alkoxide, negatively charged oxygen is attached to alkyl group. Alkyl group has a plus I effect. Due to plus I effect, negative charge will be accumulated at oxygen. Oxygen is already negatively charged here. And due to plus I effect of alkyl group, negative charge will be accumulated at oxygen. Due to this, stability will be low. Stability low means formation will be difficult, means loss of H plus will be difficult. Therefore, acidic strength will be less. Here, if we consider this type of alkoxide formed by primary, secondary, and tertiary alcohols. In case of tertiary alcohol, three alkyl groups will increase electron density at negatively charged oxygen. Stability will be very low. Loss of H plus will be very difficult. And this is the reason tertiary alcohol has very low acidic strength. Coming to phenol. Phenol, after losing H plus, forms phenoxide, and this phenoxide stabilizes itself through resonance. We'll draw resonance structures later. And during resonance, negative charge of oxygen goes to ortho, goes to para, goes to other orthocarbon atom. And due to this dispersal, scattering of negative charge, stability of phenoxide ion increases. Formation becomes easy. That is, loss of H plus becomes easy. Acidic strength increases. Now it's your turn to write. Madam, acidic strength can also be explained on the basis of stability of anion formed after the loss of H plus ion. More the stability of ion, easier is its formation, easier is the loss of H plus ion, and more is the acidic strength. Stability of any ion, any means positive or negative, any. Stability of any ion depends on charge accumulation and charge dispersal. If charge is accumulated at one particular atom, ion gets destabilized, but if the dispersed, charge is dispersed at different atoms, it gets stabilized. Next paragraph. Alkoxide ion, alkoxide ion formed after the loss of H plus ion by H plus ion by an alcohol is destabilized due to plus I effect of alkyl groups attached to alpha carbon atom. Copy from the board. This arrow shows plus I effect. So this is destabilized due to plus I effect. That is why alcohols are weak acids. That is why alcohols are weak acids. Next paragraph. On the other hand, phenoxide ion formed after the loss of H plus ion from phenol is stabilized through resonance. Stabilized through resonance. Draw everything which I'm drawing on the board. I'll click its photo and share in the group so that it will save your time.
Sir, the first one is phenol or phenoxide ion.
Wait a minute, phenoxide ion. First one is phenoxide ion. This structure, this is phenol. After losing H plus forms phenoxide. Here we're talking about stability of phenoxide ion, not the phenol. Now you can leave some space to draw these structures. I've shared photo in the group. Now write down. Now we study the effect of electron withdrawing and electron releasing groups on acidic strength of phenols. Write down. In next paragraph, in phenols, EWGs, electron withdrawing groups present at ortho and para positions increase while releasing groups decrease acidic strength of phenol. For example, I've written 5 compounds. They're all phenols. They either have electron releasing methyl groups or they have electron withdrawing nitro groups. Withdrawing groups will increase, releasing groups will decrease acidic strength. It means compound number 4, maximum acidic, then 2, then 3. This has 2 releasing, this has 3 releasing. This will be next, means 1, and 5 will be least acidic in nature. Least acidic. Next paragraph. Even photo of these structure I'll share. Apart from acidic nature, alcohols and phenols are basic as well, because they carry two LPs, two lone pairs of electrons at oxygen atom, one of which can be donated. And you know, lone pair donors are Lewis bases. Basic strength depends on how easily LP is donated, which further depends on electron density at oxygen atom. See, what you have written is, if electron density at oxygen atom is high, donation of LP will be easy and basic strength will be more, right? Continue. Due to plus I effect of alkyl groups, basic strength of alcohols is in the order tertiary more than secondary more than primary. I hope it's clear, because in case of tertiary, there will be 3 electron releasing alkyl chains. Electron density of oxygen will be very high. Donation of LP will be very easy. Basic strength will be more, right? Followed by secondary and then primary. On the other hand, electron density at oxygen atom in phenols is low due to resonance, so that donation of LP is difficult, and therefore they are weakly basic. They are weakly basic. So this was one, and that to a very lengthy property, acidic nature, along with basic nature of alcohols and phenols. Now coming to second property. The second property is also for alcohols as well as phenols. Right on number 2, esterification. Esterification means formation of ester. Right on alcohols as well as phenols. Alcohols as well as phenols react with carboxylic acids, acyl halides, ACYL, acyl halides, and acid anhydrides to give a sweet smelling ester. Sweet smelling ester. These reactions can be used as distinguishing test, right? Because product formed has a peculiar smell, sweet smell. That's why these reactions can be used for distinguishing purpose. I'm giving you 3 reactions, and there's a lot to be discussed about these 3 reactions, right? One by one. Carboxylic acid with alcohol, reversible reaction. This reaction comes under OH cleavage of alcohols. So mark according to that. In the presence of concentrated sulfuric acid, heat. Above that, this reversible reaction, concentrated sulfuric acid, heat. Product is ester, RCOR dash, and water. That a role of H2SO4. Why do we use sulfuric acid? Role of sulfuric acid. Number 1, acts as a catalyst. Acts as a catalyst. Number 2, absorbs water and prevents reverse reaction. Second equation. RCOCl is acyl halide plus alcohol. Again, OH cleavage of alcohol. This reaction takes place in the presence of pyridine, Py. Byproduct HCl. That role of pyridine. It neutralizes HCl. If you remember in the previous chapter, I told you pyridine is basic in nature, right? It neutralizes HCl so that purification of product becomes easy. Third reaction. This is acid anhydride. Reacts with alcohol. One product is ester, the other is, you can see inside the circle, this is carboxylic acid. Now I'll explain few points which will help you in questions like fill in the blanks. You have all the three reactions in your register, although I have rubbed. In all these products, there are two R's, two alkyl chains. One is attached to oxygen, the other is attached to carbon. Listen very carefully. The one which is attached to oxygen, that alkyl chain always comes from alcohol or phenol. This reactant can be alcohol, can also be phenol. Remember that. So this chain which is attached to oxygen comes from alcohol or the phenol, and the one attached to carbon, that comes from carboxylic acid or acyl halide or acid anhydride. This is similarity. So product formed is same. Alkyl chain attached to oxygen also comes from alcohol or phenol. That is also same in all these reactions. What are different? Second reactant is different. Reaction conditions are different. In first case, sulfuric acid and reversible reaction. In the second case, pyridine is used. In the third case, no special reaction condition. Third different point is second product formed is different in all the three reactions. Water in the first case, HCl in the second case, and carboxylic acid in the third case. Right? One thing more. This R attached to carbon atom can be hydrogen as well. But this R attached to oxygen cannot be hydrogen. Remember, these points will help you a lot. Now I'm telling you common name, IUPAC name of ester, and on that basis we'll take up an example for reverse calculation. Common name. There will be two words. First word will be alkyl. Second word will be common name of carboxylic acid minus ic acid. I'll dictate you. Second word will be, we'll have to derive it. Common name of carboxylic acid. From that subtract ic acid and then add ATE8. When I give you example, it will be clear. General IUPAC. Again, two words. First word alkyl. Second word alkanoate. This first word alkyl is for that alkyl which is attached to oxygen. Label it attached to oxygen. Second word will be for the remaining part. Second word will be for the remaining part. Now I'll give an example. On the basis of that example, we'll be able to name common as well as IUPAC name of the ester. Let us say it is this. First word, ethyl in both the cases. Second word, first I'll explain common nomenclature. Remaining part is carboxylic acid of 3 carbon atoms. Common name of carboxylic acid of 3 carbon atoms is propionic acid. Propionic acid. From propionic acid, we remove ic acid. What is left? Propione. Propione. After removing ic acid, then we add ATE8. It means complete common name of the compound becomes ethyl propionate. IUPAC will be ethyl, this word. This is propanoic acid. IUPAC name of acid is propanoic acid. Propanoic acid becomes propanoate, ethyl propanoate. Now I'll take one example and then we switch over to one more reaction which will take just 1 minute. Please keep on writing. Let us say this is the ester obtained and the byproduct. On the basis of products, can you tell me which of these 3 reactions has been used? First, second, or third?
Second.
Second. On the basis of byproduct HCl, we can decide this is second reaction. For second reaction, above the arrow, it is pyridine. It means this is one answer. Attached to oxygen is isopropyl chain. And this chain attached to oxygen comes from alcohol. It means alcohol used to prepare this ester is isopropyl alcohol. So this answer is isopropyl alcohol. This part comes from acyl halide. Attach chlorine here, this becomes CH3COCl. 1, 2, these are 2 reactants and reaction condition is pyridine. Right? Similarly, you may be given common name or may be given IUPAC name. On the basis of common or IUPAC name, draw structure and then from the structure write reactants. We can try even that. Let us say methyl acetate. Let us say name of the ester is methyl acetate. How do we draw the structure? First, draw the structure of second word. Second word is acetate. Acetate comes from acetic acid. This comes from acetic acid. To oxygen atom attach first word, that is methyl. Right? If I say condition is given water, then it will be reversible reaction, sulfuric acid heat. This comes from acetic acid. This comes from methanol. That's how you can decide. One more reaction, 1 minute, just 1 minute. Very, very small reaction. Right on third property. reaction with Grignard reagents. Reaction with Grignard reagents. That are alcohols react with Gr to give alkane corresponding to the Grignard reagent. Corresponding to the Grignard reagent. For example, hydrogen of alcohol R of Grignard will give alkane. Plus byproduct is alkoxy magnesium halide. Alkoxy magnesium halide. We can take an example. Methanol. Product will be ethane. 2 carbon atoms in the Grignard plus hydrogen. This methoxy will come here. Byproduct is methoxy magnesium bromide. That's all for today. Please, children, start preparing for tests. Now, there will be many tests in a row. MCQ based tests on alkyl aryl halides, subjective tests on alkyl aryl halides, and MCQ based tests on structure of atom class 11 chapter. So start preparing. Next time we'll finish the last assignment of alkyl and aryl halides. Right? Right, you can log off now.
Thank you, sir. Bye, sir.
Thank you, sir.